Hi everyone, I'm Ramakrishna Tirupati, working as a data science lead in InnoFlexus with 14 years of experience in the field of data science. I would like to extend a warm welcome and express my gratitude to all of you for joining my talk today. So the topic of my presentation is diving deep into the language of transformers. So without further delay, let's begin. So this is the agenda today. So we'll start with the challenges of traditional neural networks, including the recurrent neural networks as well. Why transformer matters, the applications of transformers, and we will deep dive into the transformer architecture, where we'll start with the input and positional embedding and the encoder modules. We have attention to the feed-forward neural networks, decoder modules, and we'll also see the cross-entropy loss function. So let's see the challenges of traditional neural networks, which is RNNs basically. So imagine you have a sentence in the storybook, right? So the cat chased the mouse. After jumbled, let's say mouse chased the cat, which completely changed the meaning. These jumbled words may also confuse, right? The same as case with the RNNs, since they fail to understand the context before and after the sentence. So traditional neural networks struggles with long-range dependencies and where there is no order and no understanding as well. So hence, if you could see the, let's say example you take, the study which was conducted over a period of 5 years, and then we have a lot of words, found that. So you can see study and found, there is a relation, right, which does not capture the using RNNs. And also it is mostly a sequential processing networks, right? And it has no attention. So every word is a unique, equal or uniform, you can say, uniform weights. So that is why these are the some of the disadvantages of RNNs and how do we overcome using the transformer architecture we will see. So transformers. So transformers are the superheroes of the AI world. So they are like a kind of detectives. They can capture hidden patterns in between the lines. So imagine having a superpower that lets you understand any language in the world. So that's basically what transformers do for computers. They use attentions as a backbone. So what is attention? So as a human, when we read a paragraph, our eyes usually catch and pay attention to only for a few words. For example, words like here you see rainbow, arch, vibrant, display. So because we understand the language, we naturally focus on the certain words. This is similar to how attention works in the transformers. Attention is like a pair of binoculars that helps transformers see far and wide, capturing the long-range dependencies and understanding the big picture. So why transformers matters? So transformers were first introduced in 2017 by Google and University of Toronto in a research paper called Attention is All You Need. This paper proposed a new architecture called Attention is All You Need, which is the transformer model architecture. So now transformers have a revolutionized in AI by introducing new way of processing sequences. So they can be parallel, they can scale efficiently, and they can also they can have attention to focus on right parts of the sentence as well. Just like focus on the most important words in a story. They help them understand context, a relationship, and long-range dependencies. So there are some of the applications of the transformers we will see. So these are few applications which I mentioned, but of course many. So we have few applications like sentiment analysis classification, machine translation, NER models, the text summarization, and image captioning, object detection, ASR or text-to-speech conversions, and personalized content recommendations, chatbots, the recent trends of generative AI, including the ChatGPT, Bard, or Llama, etc. So these transformers are not just in NLP. So people have a myth around the They can be used in only NLP, but it is not only in NLP. It can be used in computer vision. It can be used in text-to-speech recognition or audio as well, anything, right? So that's what it is. So what is a transformer? So the transformer architecture consists of two main components, which is encoder and decoder. So here in this example, we are translating this particular sentence to English. I am a student. So the encoder takes a sentence of the sequence of words as input, converts them to a context representation. The decoder takes the context information learned by the encoder and generates the output sequence. The original transformer architecture, as you can see here, we have a 6 encoders stacked together, and then similarly we have a stacked 6 decoders. The 6 encoder layers are stacked because they allow the model to capture the complex contextual relationship between the input elements. And the decoders are stacked together, enabling the model to generate the better output sequences. So now this is how a transformer architecture looks like. Let's see how encoder decoder look like if we go inside. So encoder has a 2 layers associated with it. So first is the multi-head attention, where it captures the contextual relationship within the sentences, which is a core component of the entire block. The second one is the feed-forward neural networks, where it means that it relationship between the input and output. So there is a difference of the multi-head attention or the attention versus the feed-forward neural networks. So feed-forward neural networks understands the relationship between the inputs and outputs, but the attentions are identifying the relationship within the input sentence itself. So that is the major difference. So similarly, decoder has three layers associated with it. So first is called masked multi-head attention, which ensures that it does not see any future information when it is predicting the output, preventing the model from cheating or relying solely on the context information from the encoders. Then second layer is the context-aware attention layer, which is also called as multi-head attention. Takes the context information learned from the encoder and used it to learn the relationship between the previous tokens and the context information from the encoder. Then third layer is the again feed-forward neural networks. It learns the relationship between the input and outputs. So let's take an example. So have you ever tried to translate a sentence from one language to another? So it can be tricky, especially if the two languages have a different grammar rules or vocabulary. Let's take an example here. I went to the store. Translation of English to Spanish. Here, how is it processed? Before we pass to a transformer architecture, there is some processing that will happen usually. So that's what we will see here. So I went to the store. Right? So every sentence, whenever you get a sentence to the encoder, it breaks down to a small pieces of information. Here we call as a tokens. So we have a tokenizers. So it could be a BPE or word piece tokenizer. So using that, it breaks down into a small pieces of information, which is called tokens. Since machine does not understand the text, so now we break down the, let's say I went to the store, it break down to I went to the store. So since machines does not understand this text, we need to convert them to numbers. So once we have the numbers, so here you can see every token will be represented by a unique ID in the dictionary or a vocabulary. So we call as a dictionary, but in the machine terminology, in the NLP or any transformer terminology, we call as a vocabulary. So vocabulary is something where from a training data, you see how many tokens that appears, you add to a text file that becomes your vocabulary. So that is a naive transformation, but it does a lot of processing as well, because if you put every token to a text file, it will become a large and large. So we need to reduce that also. There is a separate concept on that. So once we have the tokenization, so here if you can see, I will be represented by a unique ID called 142, and similarly Vent is represented by a 975 and so on. So once we have the tokens, how do we convert them to next further embeddings techniques? So every token here would be projected to a 512 vector, but they are varied depending on the specific architecture. So in the first paper, attention is all you need, have a 512 dimension size. They are initialized again randomly. These are the parameters at the beginning. These are the parameters which are initialized randomly at the beginning, and they are learned with the training data and using the back propagation. So as you can see, every token now is projected onto a 512 dimension vector. So you can see here 142 is projected into a 512 dimension, and similarly went also, and similarly 2 also the store. So every word is projected onto a 512 dimension vector. If this vector, you can see this vector is actually a 512 dimension, which I can't keep here, but usually it is a 512 dimension. So let's say if we have a 500 input tokens and we have a 512 representation, the number of parameters will become here 512 into 500, which is almost 256,000. Imagine these are the parameters only at the input embeddings, right? So that's how it will pass. And then once we have the input embeddings, it combines with the positional embedding. So the positional embeddings, why it's required? So if they are like a GPS for words, so they help the machine to understand the order of the words in a sentence, right? And then if the words are spelled differently or out of order. So let's say cat sat on the mat has a different meaning than the sentence the mat sat on the cat, right? So because if we add a position to this, it understands which word is at which position. That's why the positional embedding is really important in that. So once we have that, so positional embeddings, how is it calculated? Using a sinusoidal or cosine signals, right? To capture the information where it has a variable called POS. There are two values. POS stands for position and I stands for the index. Let's say if you are converting, like let's say 140 to I, the first I is at a position 0, and then I will become like 0, 1, 2, 3, 4, and then 512. So since you can vary like that, so it will start with that. So then finally you will get the positional embedding 0, 1, 0, 1, and then for the first one, because sine 0 is 0 and then cos 0 is 1, something like that. And then next vent also you will get the positional embeddings. So here that's how positional embeddings also will have a 512 vector dimension. So once you have positional embeddings, we have the input embeddings, we will combine them using the operation plus operation. So then we get the final input embeddings which we pass to encoder. So which has a contextual information now. So now we have understood how input sentences are processed before forwarding to the encoder. Let's see the encoder in detail now, right? So as I mentioned earlier, encoder has a two layers. The first one, multi-head attention, which learns the relationship between the input sentences, how the words or tokens, you can say, are related to each other. And similarly, the second one, feed-forward neural networks, which builds the strong relationship between the input and outputs. So let's take a deep dive in each of these layers. So we'll come to the multi-head attention. So multi-head attention, we will learn what is the attention first, and then we'll be back to multi-head attention. So attentions are like a kind of flashlight, right? So which understands which words are really important in a given sentence and what is the relationship between the words. So in this sentence example, she is eating a green apple. So when we hear this sentence, our brains automatically pay attention to a certain parts of it. Like for example, when we hear the word eating, our attention or our brain is drawn to the idea of eating what? Is it apple, banana or orange? Something like that, right? So this is what exactly attention does in the transformer architecture. So let's see more examples to get a more understanding what attention is. So here I went to the store. So you can see the output visualization of the attentions. How is it really look at? I went to the store and you can see at the store, I bought a fresh fruit is an example I'm taking. As if you see, word went has given more weightage to the words like to store. So it means when you can relate when to store. So which means that that is how it understands it, right? And similarly, you can also look it as a word, right? It has a given importance to a tokens called the store. So if you look all the words, things even more complex. As you can see, how relationships are learned between the tokens within the sentences. Let's take one more example to illustrate. So here is the example. At the store, he bought a flowers, candy, jewelry, and so on. So we can notice here again, bot has a more attention to flowers and candy. But how attentions are learned between these words? Using three matrices. Did you hear it correctly? Yes. Using three matrices. As you must have learned in linear algebra, matrix also can help you. Do you ever think of matrix could solve this entire problem of the universe? Yes, only three matrices, which is query, key, and values. This is the secret to attention. So what are those QKV, which is called as the queries, keys, and values? So these matrices are like eyes, ear, mouth of a transformer architecture. So they allow the network to see, hear, and understand the relationship within the input sentences. So let's take an example or take a look how we can interpret QKV with few examples, and then later we will calculate how it will be done. So let's say in YouTube, you search for funny cat videos, and keys would usually become category, emotion, genre, and duration, right? And then values would become ideally the actual videos, right? These are like actual videos. So you can, when you user or when a person really search for a query called funny cat videos, it understands how much emotion or how much what is the category that it is for, and what is the genre, and what is the duration. So all this they become a keys, and the values will become the actual information associated to that particular video. That's what you can interpret, right? And now one more example here. I went to the store is what is an example that I'm taking. Let's say if you are calculating attention to a store word, the query would be a store here. The keys and context are nothing but the keys, context information of I went to the store, right? So it has become every individual relate with respect to store. What is the context information will become a key, and the values are nothing but actual information of the word itself. That is what is the value. So let's see how these matrices are formed, right? So let's take an example. So now we have got the input embeddings. Now these input embeddings, once we have the positional embeddings, and then how it will be passed to an attention, we will see. So we have these embeddings, which is in the 512 vector dimension. You need to remember that. So then now once we have this, there will be one vector which is called as a WQ, which is in a dimension of 512 by 64, right? And this is initialized randomly again, this 512 rows and 64 columns, right? So with that, we initialize that, and then once we multiply every embedding, input embeddings with this WQ matrix, we get the queries. And similarly, we initialize the WK, and then we get the query key matrix. Similarly, the WV, which is 512 by 64 again, and then we get value matrix. So, but did you notice this is a 64 in dimension compared to a 512 dimension? To reduce the complexity, the computational complexity, the paper is introduced basically from like 64 is the ideal number, but that can be tried out, and then that can be also a customized, that's an hyperparameter. We can change it as we go, right? So let's move on. So once we have this matrix, so I told you these are initialized randomly, right? So now the total parameters here at this moment, it becomes again, compared to the earlier, only at the input embedding, at this point, we have this total parameters called 512 into 64 into 3, which will become 98K. So that's how. So here, once we have the keys and query vectors from the initialized matrices of WQ, WV, WK, and then we take the query and key vector, and then we see how is it like. Let's take an example of how attentions are calculated for the first word I. If we want to calculate the attention for I, the query vector of the I will become the query vector, and then keys and values for the vectors for all the words. And then if you want to calculate for the vent, the query vector will become vent, and then the rest of all the vectors will become the keys. So here we will calculate the attention for the I token. Let's take the query vector for I and calculate the cosine similarity between the query vector and the key vector for all the tokens using the formula called Q into K transpose. So what is Q into K transpose? Ideally, it becomes the cosine similarity between they are individual vectors, they become a cosine similarity. So we try to see what is the similarity between the queries and keys. So now once we have the cosine similarity, you can see how these like keys and query and Q1 into K1 will become element by element again and then sum it up. So 120 and then Q1 into K2 will become again 52, then 46, then 34, and then we have a 110. Right? So once we have these values, once we have the similarity scores, then we will divide by the square root of the attention size. So why? Because why do we need to do division? Do you ever thought of that? So this something, because if we have a larger number, if you want to deal with the larger numbers, sometimes there will be a larger and larger numbers, right? Sometimes this is just one. I gave you an example of 5 words, but if it has multiple tokens, right, then it becomes a lot. Numbers could be larger and larger. Then it can lead to numerical stability issues. So to reduce these numerical stability problems, we reduce this dimensionality of these vectors, of these numbers basically, and divide by the square root of dk. Dk is nothing but what is the attention size or attention embeddings, the query or the key or the values, what is the vector size? That is 64. At this point, sorry, it is a 512 is mentioned, but it is a 64. So square root of 64 will become 8. And then you divide every value of this similarity score divided by 8, then you will get the actual value, right? And then we calculate this, since we want to know what is exactly the proportion that will come. So we take the softmax values. Softmax values which will ensure that what is the proportion of this particular key or the word is actually related. I to I, how much is related? I to went, how much is related? What percentage is related in the way? And I to 2, how much related? So that is what is the attention. I is paying to attention to what now here? I to I. Actually, sometimes you may also pay attention to yourself, right? So that is also possible, and many times it is possible, and the other few times it may not be possible every time, right? So I to here you can see after leaving the I word, and then it is paying attention to the store, right? The word store. So after the softmax probability, we calculate the V. So we take the value of each individual vector, and then we multiply these values with the value vector, and then we get the actual weighted value vector, which is the weighted attention information of the respective words with respect to I, because we are calculating the attention for the I word. So once we have this information, as you can see here, the darker means it is more weight, and is lighter color means it's lesser weight comparison, right? So that's how the information is stored. And once we have all these values, we sum it up. So that is what is the sigma of, that means summation of all the individual information with respect to I, we sum it up, and then we get the final vector, final attention vector we call. So that is what is the final attention vector for the individual token called I here. So for the I, we got one attention vector, right? So once we have the attention vector, but problem is we want to send it to the next layers also, right? So we want to get back to this similar size that we are passing, right? Because the input dimension is 512, but the output dimension also should be 512, because the next layer expects also 512 as a dimension, right? So that's why you may need to have similar dimensions. So hence we need to convert back from 64 to 512 using the one matrix called. This is also again initialized randomly, which is called WO. So that is initialized randomly. Once it is initialized randomly, so we multiply the query attention vector with the WO, and then we get the final vector, which is called as a attention vector with respect to that word. But now, once we understand this final, we got a 512, right? So then, but we have a multi-head attention. What is multi-head attention? The multi-head attention is we have an attention. We have like almost 8 attention heads in parallel. So why it is required? So it requires multi-head attentions, because just the reason is it learns in a more complex relationship within the input sentences, right? So when it learns the multiple input sentences, you get every time you get a 64 attention vector for each individual word. So then we also have the weight vectors, and then we multiply with this. So if you have 8 attention vectors and then 8 weight matrix, they multiply with that, and then finally you get which is the input vector, which is to the next layer, which is the 512 in dimension, which is the attention of the word, which is with respect to I, will become your final vector. So once we have this, so we will move on to the next, which is basically a layer normalization. So if, as you can see here, the add and normalization, which is ideally very, very important. So add and normalization, why it is required, right? Just to ensure we don't get the problem of vanishing, because if you are adding and many layers and layers, right? So sometimes we may get a vanishing gradient problem. Hence we add the inputs to the so to get rid of this vanishing gradients problem, so we add the input layer also to the output of every attention, and then we normalize those values. That is what is the layer normalization does operation for you. So we take, like, let's say example, we have the input embeddings to the before the attention head, and similarly after the attention head also we got the context vector, which is the attention context vector, and then we sum it up using this formula x minus mu by sigma, which is the traditional normalization, and then we have a two parameters called gamma and beta. So these are again hyperparameters. So we sum it up and then we get it, and then once we have like some value of like mu and sigma based on this vector, and then we get the final vectors once you add the normalization. So this, then now you can see here, once we have the layer normalization vector is calculated, then we pass this to a feed forward layer, which is the next feed forward neural networks. So every token, now you can see here, I went to the store. Every token will produce one single vector of 512 dimension in length, which will be forward to the feed forward neural networks. So in the first architecture, while we have two layers, one hidden layer is like 1024 neurons, and the output layers just to match with the next layer, next attention layer or next encoder expects the 512 as the dimension. So output layer should have the 512. If you are changing this number, but you need to, you can also have a one more matrix to multiply and then match that if you want to change. But ideally you can go with the number that we specify, 5024 and 512, right? Then now once we have this 512, then we get the using the ReLU as an activation function ideally here at this moment. So we get the, again for each individual word you get again one single output, you can see with the 512 dimension. So once we have this output, so how, like, because now we have studied only one encoder at the moment, right? So now in the encoder, you can see here, we have passed the input to, at the end we see the context vector, and then this context vector, it will be passed to the multi-head detection, again next encoder, and then this will be passed subsequently. So as you can see here, there are a lot of encoders, like as I mentioned earlier. So there are 6 encoders in the first architecture that the information will be passed every token to token. That's how the encoder architecture will be passed. So now, since we have understood the encoder architecture, let's start with the decoder. So decoder, like encoder, we have 2 layers, like we have 3 layers, but the 2 layers are actually common. You can see here, the multi-head detection and the feed-forward neural networks. But there is a one extra, which is the layer which we call as a masked multi-head detection. So in the masked multi-head detection is to make sure that it should not see the future tokens. So decoder operates in a way that in an auto-regressive mode. So whatever it is predicting the output, it will be again passed as an input to the decoder at every step, and then that as a next step it will produce to the decoder. But decoder, when you are passing from the output token to as an input, it is an auto-regressive mode, right? So sometimes it may be a possible that it may see the future tokens, right? So hence there should be a masked self-attentions which makes sure that not to cheat the system or not to see the future. That's what we require, a masked self-attention in every decoder. At any point of time, we don't want to see the future tokens. That's what this makes sure that, right? So now think of a machine translation where we would translate the input sentences I went to the store into Spanish. Encoder only generate the contextual vector, but decoder job is to decode the job using the context information from the encoder here. So you can see the context information from the encoder here is passed to a decoder as well with to the multi-head detection. So now let the first decoder, it takes the input from the encoder, keys and values are generated here, and the previous generated output embeddings of the keys and values. With the last encoder we have the keys and values, and those keys and values are passed to the every decoder. You can see here, right? The first decoder, the context information is passed from the, context information is keys and values of the last encoder is passed to the first decoder, and the previous generated output embeddings are passed to the decoder, the first decoder, and the decoder will be passed to the next decoder will take the information again, keys of values of the last encoder, and then we will take the previous decoder information, and then similarly like that. And then we have the linear and softmax layer to get the output, actually what is the expected output. So I went to the store, right? So we are expecting something at the output, fui all and tienda, right? So this is what a Spanish word, Spanish sentence. So I went to the store, right? So now what is it like, how it is in the first go, how it will happen, because we do not have any previous generated output, right? So this is how it will happen. So example, if we don't have any output in the initially, we start with the start of the sentence as a token. That is a separate token which is in the vocabulary in the transform architecture. Yes, the token called as a SOS, and similarly the end of the sentence is called as a EOS. So these are the special tokens which is added in the vocabulary. Whenever there is a no token that is there in the output, so decoder starts with the SOS as a token. So once the SOS token is done, so similar fashion how input embeddings are calculated, like the positional embeddings and all. So same information how like the output also, these information will be added in the positional embeddings, and then that will be added, and then that will be passed to our decoder, the first decoder. So now once we pass, then we subsequently pass to all the decoders, and finally we get the output called FUI. So now at any point of time, a single token is produced at the decoder. So now once the FUI is produced, now FUI is passed back to the decoder is input again at the beginning, and now we can see along with the start of the sentence token and the FUI token is passed to the decoder, and then subsequently, and the decoder will produce here as a word, right? And then similarly, now these will be passed to the decoder, and subsequently here is the third token output. You can see la, right? This will again take as input along with the previous generated tokens, and then fourth will be produced. You can see here as a tienda, right? And then now this will again take as input along with the previous generated will be taken, and then they will produce in the decoder. The final token that will produce is the EOS. So whenever there is a EOS output is generated, then it will stop that iteration. So the decoder job is to produce the output. So whenever there is it sees the EOS as a token, then it will stop that iteration. That's how the decoder produces the output, right? So now once we we have understood, but how do you ever wonder how predictions will happen at the output? So the decoder only produce, like decoder also produce the attentions, right? But the problem is how predictions, the attention vectors of the decoder also will produce the output in general, right? The FUI is what we are trying to predict. So now we use something called as a linear, which is artificial neural networks plus softmax, okay? So it will generate the softmax probabilities of all the vocabulary words, you can see, right? So they will do once the softmax actual probabilities, like entire vocabulary, like you hear that the first word I said is FUI. So the FUI is like the maximum probability that it will come across around the entire context, entire vocabulary, then that output was the produced. That's how it is produced using these linear and softmax functions, right? So now, but do you ever think like how weights and parameters get updated using a softmax loss function, right? So here I am illustrating with the cross entropy. So there could be several loss functions like KL divergence also you can use, but I'm illustrating with the cross entropy loss function. So initially they will be with the random weights, right? So you have initialized every step we initialize randomly, and assume the some output probabilities that the softmax probabilities are produced, like as mentioned here. So you can see in the step 2, step 1, step 3, right? At any moment, because we have the actuals also, we have the predictions also at any point of time. And now we compare this like at each step for each single sentence, step 1, step 2, step 3, step 4, step 5, right? So now we combine with all the tokens using the formula of the cross entropy minus sigma of logarithmic of probability of the predicted value, right? So now if you see the loss, how it will like logarithmic of, you can see here log of 0.24 in negative of, right? So and then it is the step 1 and step 2, step 3, step 4, step 5, right? Like this it will calculate, and then finally now you can see it's the logarithmic of calculate, and then we sum it up, sigma you can see here, right? Sigma of the total tokens you have to sum it up. So we get the final value is the 7.47. So now with this loss function, I would say that the parameters get updated using the derivatives and the partial derivatives, right? So with the help of at every point you compute with the w minus the learning rate into the derivative of the loss function, which is this loss function, cross entropy loss function, and then the parameters are updated. So at the final we get the finally the optimized weights once we have the loss optimized, right? So that's how the weights are updated. So that's the end session. So with this, I would like to take this opportunity to thank you for your interest to learn about transformers, which is revolutionary in the NLP.